started learning about buffers in level 68, so now we're going to talk about what's called buffering capacity, which is the amount of protons or hydroxide ions that the buffer can absorb without a significant change in pH. So where, like we kind of saw between examples 2 and 3, how the pH hardly changed whatsoever. A buffer with a large capacity contains large concentrations of buffering components and so can absorb a relatively large amount of protons or the hydroxide ions without showing a pH change. Because the pH of a buffered solution is determined by our ratio of the hydroxide of the conjugate base to the acid's concentration, the capacity of a buffered solution is determined by the magnitudes of both of those concentrations. So we're concerned about the numerical values. Okay? So for example 5, we want to calculate the change in pH that occurs when 0.01 mole of gaseous hydrochloric acid or hydrogen chloride is added to 1 liter of each of the following solutions. So we're going to have to do this for solution A and for solution B. Okay? Well, before we do that, let's go ahead and calculate our initial pH, because we don't know a change unless we know what it initially started at. So for the initial pH, we're going to use our Henderson-Hasselbalch equation, where pH is equal to the pKa plus the log of the A minus concentration over the HA concentration. Okay, so we'll have the negative log of Ka, because we're dealing with acetate and acetic acid here, and this Ka was given back to us in example 2. So that Ka is 1.8 times 10 to the negative 5 plus the log of the concentrations. And so both concentrations, both solutions will actually cancel out because it's 5 molar acetic and 5 molar sodium acetate for solution A, and 0.05 molar for the acetic and 0.05 molar for the sodium acetate in solution B. So that ratio is going to be 1 for both solutions. So our initial pH is going to be the same for both solutions. So when you solve that out, the initial pH is 4.74. So we're going to need this later on. Okay. Now let's think about solution A only. Okay. But before we do that, we're going to have the same major species in both solutions as well, so we can always think about those. What's involved here? Well, we have our acid, and because it has a Ka, it's weak, so it doesn't completely dissociate. We have the sodium from the salt plus the acetate ion from the salt. We have water, because it's an aqueous solution, and we have our HCl being added. So we're going to have protons added, and we're going to have chlorine atoms added. Okay? Well, before we do this, we have to use up these protons. Just like we did the hydroxides back in example 3, we're going to have to use up those hydrogens first before we can figure out what this is going to do. So the water is no longer important. The chlorine, not really important. The sodium, not really important. So we're going to actually do the backwards equation for dissociation. So we want to turn some of that hydrogen proton back into the acid. So we're going to have the proton plus our acetate, because those are floating around in there, and turn it back into the acetic acid. Okay? So before the reaction, if this is all happening in 1 liter, then our molarities given for the solution are also the moles in the solution. And please don't forget, we are doing this for A. So if we have 5 moles, molar solution of the acetic acid, we have 5 moles to start. And if we have 5 molar of the sodium acetate, that means we have 5 moles to start for the acetate. But we do not have, oh, yep, we do, sorry. We have 0.01 moles of the HCl. So since it's going to completely dissociate, we know that will be for the hydrogen. Okay, so we need to get rid of the hydrogen, so I'm going to subtract the 0.01 from the reactant side, both of them in the reactant side, and we're going to add it to the product side. So now we have 0 hydrogen left over, protons. We have 4.99 moles of the acetate and 5.01 moles of our acid. Okay? And it's a 1 liter solution. So those are going to be our polarities. So now we can figure out our new pH using the equation that we used before. Okay? So the pH is going to be equal to the pKa. Well, log of 1 is 0. And so we're just going to plug in what our initial pH was, the 4.74, as our pKa. We don't need to solve that again. Plus the log of our ratio. So it's conjugate base over acid. So we're going to take our conjugate base number, the 4.99, over the acid, the 5.01. So the new pH is going to be, when you solve it out, 4.738, which with sig figs that will still be 4.74. So this had no change from the original, because we originally had 4.74. It's still basically 4.74, so there's really no change. Let's do this for B now. So for B, we're still going to have our hydrogen being used up, but we're going to use the other concentrations now. So we'll have our same equation where we're using up the protons and making acid. And this time we'll still have the 0.010 mole for the H+, but this time our concentration of the sodium acetate is 0.05 molar. So we're just going to say that that's moles because it's all in 1 liter. And the same for the acid. So we're going to subtract the 0.01 from the reactant side and gain it on the product side. So now we have 0 for the H+, now we have 0.04 moles for the acetate, and for the acid we have 0.06 moles. So again, it's in a liter solution. So these are our concentrations. So for our new pH, for part B, or solution B, we're going to use the same equation, and our pKa is still the same, the initial pH, plus the log of our ratio. And so we're going to have our acetate, our 0.04, over our acid, 0.06. And so when you solve for this new pH, the pH is 4.56. So the change in our pH this time is a difference of 0.18 from the initial. Okay, so this is showing us that the higher concentration you have in a solution, in solution A we have 5 molar versus solution B we have 0.05 molar. The higher the concentration of the buffering components, that means that the solution will resist a change in the pH better than if it had smaller amounts. So for optimal buffering, we have that occur when the concentration of the acid is equal to the concentration of the conjugate base, like we had just now in our example. At this condition, the ratio is most resistant to change when we have to add the hydrogen, the protons, or the hydroxide ions. So when choosing the buffering components for a specific application, we want to pick the one that has the ratio equaling 1. because by doing that, then when it equals 1, we know that the pH is then equal to the kPa, or excuse me, the pKa. So then we could keep the pKa of the weak acid as close as possible to the desired pH, so we'll have less of a change. So we'll need to pick, in example 6, which solution works best, okay? So a chemist needs a solution buffered at a pH of 4.30 and can choose from the following acids and their sodium salts. And they're all listed with their Kas. So we need to calculate the ratio HA over A minus required for each system, so the acid concentration over the conjugate base concentration, to see which will work best. Okay. Before we get started, we're going to go ahead and figure out if we have a pH of 4.30, what is the concentration of the H plus here? Okay. And the reason why we're doing this is because of our rearranged expression. The H plus is equal to the Ka times the acid concentration over the conjugate base concentration. So the smaller that this ratio is, the better, or the closer to 1, the closer to 1 this ratio is, then the better the buffer solution will be. Okay? So let's figure out our H plus first. H plus, remember, from chapter 14 is take the antilog of the pH, and so that is 5.0 times 10 to the negative 5 molar. Okay? And so let's go ahead and figure out our ratio, where we're going to use the Ka, the Ka as the bottom number in our ratio, and the hydrogen that we just saw for as the top, because, sorry, I forgot to mention this. If we rearrange and multiply over, so we have 2 on each side, if we take the H plus divided by the Ka, that is equal to the HA over the A minus. Okay? So that's why we're going to take the H plus we just saw for over the Ka given. Okay? So I'm going to just letter these A through D, because I don't want to write out chloroacetic acid. So we have 5.0 times 10 to the negative 5 over 1.35 times 10 to the negative 3. So the H plus over the Ka for that first one. And that is equal to 3.7 times 10 to the negative 2. So less than 1. Okay. For B, we'll still have our 5.0 times 10 to the negative 5 for the concentration of our H plus, but now we have 1.3 times 10 to the negative 5 on the denominator, and that is equal to 3.8, bigger than 1. C, we're going to take our H plus divided by the new Ka, which is 6.4 times 10 to the negative 5, and that is equal to 0.78. So that's a lot closer than the other two to 1. And last but not least, for the hypochlorous acid, divide by that Ka, 3.5 times 10 to the negative 8. Our answer is 1.4 times 10 to the negative 10 to the positive third. Sorry, that's 1400. So, which system works best? Well, we need to pick the one closest to the value of 1. Well, the closest value would be C, the benzoic acid, because that's 0.78. Everything else is too far away from 1. So we would pick the benzoic acid and its sodium salt to be the best choice for buffering a solution at a pH of 4.30. So if you figure out the concentration over the Ka and pick the one closest to 1, the pH will have the least amount of change. That's it for level 69. Our problems this time are numbers 11, 39, 47, and